You know, we plug stuff into the wall every single day and just don't think twice about it. But have you ever really stopped to wonder what's actually going on inside that socket? Well, it turns out the AC power that runs pretty much our entire lives has this hidden layer of complexity that is just absolutely fascinating. So today, we're going to unplug that mystery.
So let's start with something we all know, something super familiar, the humble wall socket. It looks simple, right? But believe me, it's the gateway to our first big puzzle.
So if your home runs on, say, 230-volt electricity, you'd probably assume that's what you're getting, right? A nice, steady 230 volts? Well, what if I told you the answer to that is a hard no? It's not even close. That number is really just for convenience, because the reality is way more dynamic. Okay, so here's the heart of the problem. With AC, or alternating current, the voltage isn't some flat, constant line. No, it's a wave, a sine wave to be exact, that's constantly swinging from a positive peak all the way down to a negative peak and back again, doing that 60 times every second. So how on earth do you slap a single number, like 230 volts, on something that's literally never standing still? The answer, and it's a really brilliant piece of engineering, is something called the RMS value. This is the key. This is the concept that lets us talk about AC power in a way that actually makes sense for the real world. The phrase to lock onto here is effective value. RMS basically gives us a practical, usable number that's equivalent to a DC, or direct current voltage. Think of it like this. The RMS value is the amount of DC voltage you'd need to generate the exact same amount of heat in, say, a resistor. It's the useful, work-doing value, and it's what pretty much any multimeter you pick up is going to show you. All right, so if 230 volts is just the effective value, what's the actual peak voltage that's zapping your devices every cycle? Get this, it's way higher. The peak is the RMS value times the square root of 2. So that means your friendly 230-volt outlet is actually hitting a peak of around 325 volts. Yeah, that's the real top of that electrical wave. Okay, so we've kind of cracked the voltage mystery, but that just opens up the next can of worms. When we start talking about power in AC circuits, it turns out it's not just one thing. It actually has 3 different phases. Let's meet them. Remember in simple DC circuits, power was just volts times current, P equals V times I? So easy. But in the world of AC, especially when you've got things like motors and transformers in the mix, that formula doesn't even begin to tell the whole story. There are other things going on. First up, we've got real power. We use the letter P for this one. Now, this is the power you actually care about. This is the good stuff. It's the energy that gets used up to do actual, useful work. You know, the light coming from your lamp, the heat from your toaster. This is the power that's measured in watts, and it's what you actually get billed for. Next, we have reactive power, or Q. Now, this one's a little weird. It doesn't actually get used to do work. Instead, it's the power that just kind of sloshes back and forth in the circuit. It gets stored up in the magnetic fields of things like motors and then released back into the grid. It's absolutely essential for those devices to run, but it's not contributing to the final useful output. And that brings us to our third phase, apparent power, or S. This is the whole shebang. It's the total power that the grid, the whole system, has to be able to deliver. Think of it like this. All the wires and all the generators have to be beefy enough to handle this total amount. That includes the useful real power and that sloshing reactive power. So you've got these 3 different types of power. How do they all relate to each other? Well, it turns out they fit together perfectly in this really elegant concept called the power triangle. And check this out. It's literally just the Pythagorean theorem from high school geometry. Real power and reactive power form the 2 legs of a right-angle triangle, and the apparent power, that's the hypotenuse. It represents the total magnitude of power that the system has to be ready to supply. Okay, so let's do a quick recap here. We've got real power in watts that's doing the actual work. Then there's reactive power in VAR, which is that stored energy just oscillating in the system. And finally, apparent power in VA, which is the total load the system has to bear. 3 different things, all working together. So why does this distinction even matter? Why do we have to split hairs between real and apparent power? Well, it all comes down to one single critical idea: efficiency. And we measure that efficiency with something called the power factor. It's super simple, really. It's just the ratio of the useful real power to the total apparent power being supplied. You can think of it like an efficiency score for your electrical system, from 0 to 1. It tells you exactly how much of the power being sent your way is actually doing something useful. So a perfect power factor of 1.0 means every single bit of power the utility sends you is doing useful work. This happens with simple things, like a basic heater. But the moment you plug in a motor, the power factor drops below 1.0, and that means you've got all this reactive power sloshing around, making the whole system less efficient. And here's the bottom line. This is why it all matters. A low power factor is bad news for everybody. It means the utility company has to generate and push more total current through all their wires just to deliver the same amount of useful, real power to your home or factory. And that extra current, it doesn't do any work. It just heats up the power lines, which is nothing but pure wasted energy. So starting from just a simple number, 230 volts, we've uncovered this whole dynamic world of peak voltages, invisible reactive forces, and crucial efficiency ratings. It just goes to show you that inside the most everyday things, there are these complex, elegant systems quietly at work. And it really makes you wonder, right? What other invisible forces are out there, hiding in plain sight, shaping the world all around us?